In the 1990s, computer networks exploded across the globe, bringing with them a wave of intense digital optimism. The internet was viewed as an open, unrestricted gateway to vast, nonlinear information. Because of this rapid expansion, a baseline assumption took hold in educational design. Translating complex print materials into digital, hyperlinked formats would automatically enhance a student's ability to learn. Spiro's cognitive flexibility theory argued that mastering complex subjects requires revisiting concepts from multiple perspectives. The hyperlink mapped perfectly onto this, seemingly allowing for instant, frictionless contextual shifts, jumping effortlessly from one perspective to the next. The perceived synergy between theory and technology established a new standard, the expectation that digitizing a text would result in cognitive flexibility. But to understand how people actually read online, we must look past the abstract theory of the web and examine the physical hardware they used. Students were not floating through an ethereal network of data. They were sitting in rigid postures at desktop workstations. The boundless theoretical node network was trapped inside a rigid 15-inch rectangular frame. Within this restricted viewport, connections became tangled. Context was hidden behind drop-down menus, and the visual space was severely cramped. Empirical evidence from human-computer interaction psychology reveals a sharp contrast to the early optimism. Digital interfaces often slow down and impede complex reading tasks. The physical limitations of screen-based reading induce a hidden cognitive load. This load actively disrupts a reader's ability to integrate multiple sources of information. In 1997, researchers O'Hara and Selin designed a study to isolate this problem. They asked participants to summarize a 4-page science report, comparing those reading on paper against those reading online. The physical workspace for the two conditions was entirely different. On a desk, a reader can spread out 4 pages in a wide grid. On a screen, the reader is restricted to viewing a fraction of a single page. This wide grid enables spatial mapping. Readers unconsciously memorize the physical location of key facts across the laid-out pages, knowing instinctively that a specific data point is in the top left corner of the 3rd page. Laying out physical pages is an automatic, zero-friction action. It requires almost no attention, meaning it does not interrupt the cognitive process of actually thinking about the material. Sequential scrolling on a computer requires the opposite. The brain is forced to abandon its global spatial map of the text and dedicate active concentration entirely to the mechanics of navigation. Desk space is a critical cognitive offloading mechanism. Forcing all information to be viewed sequentially through a single screen eliminates that mechanism entirely. The O'Hara and Selin study identified a second major behavioral difference: the physical mechanics of note-taking. In print, handwriting creates a perceptually distinct layer. The blue ink exists physically parallel to the black printed text. Because these layers are distinct, the brain interleaves reading and notes almost simultaneously, smoothly shifting focus back and forth. Digital note-taking introduces immediate mechanical friction. The reader has to move away from the source text entirely to type inside a visually separated, disconnected window. The interface turns annotation from a seamless learning aid into a highly distracting, cognitively taxing secondary task. To test exactly how these friction points impact comprehension, a 2003 study by Macedo Ruette and colleagues observed students reading highly complex popular science materials. The subject matter was a dense, multi-document report on the abortive drug mifepristone and its medical and political implications. In the print version, the layout placed the main feature text securely in the center. It was flanked by physically adjacent supporting documents, infographics, and data tables, visible on the same spread. The web version featured the exact same text, but due to the boundaries of the screen, those supporting infographics were hidden behind hyperlink menus. Online readers had to execute a cumbersome series of mechanical steps, clicking to spawn a pop-up, adjusting the window size, and activating a zoom tool just to read the caption. The resulting data revealed a clear split. Primary text comprehension was equal across both groups. But the web users suffered drastically lower comprehension of the supporting documents. Researchers call this the what's behind the door syndrome. When secondary information is hidden behind a hyperlink, the intertextual connection, the visual relationship between the claim and the evidence, is severed. Poor web architecture erased secondary evidence from the reader's cognitive map. The Macedo-Roy study also uncovered a dangerous paradox regarding how students evaluate their own learning. These identical bars show user satisfaction ratings. Despite poorer test performance, the web group reported high satisfaction. But overlaying their hidden cognitive state and actual test results reveals a massive spike in cognitive load and a sharp drop in comprehension strictly in the web column. The students' familiarity with technology masked the friction of the interface. They enjoyed the interactive experience while remaining entirely blind to their own comprehension deficits. For educational tech designers, this is a clear warning. Positive user attitudes and high engagement metrics do not prove that effective cognitive processing is taking place. The current bottleneck stems from the specific spatial and perceptual design paradigms used to organize online information. Supporting cognitive flexibility online requires moving past the simple hyperlink for managing complex data. Interfaces must mimic the physical offloading of a real desk. That means building infinite spatial canvases for documents to sit side by side, providing distinct, integrated layers for annotation. Future digital learning environments must prioritize structural visibility over simple interactivity. The entire map of information needs to be visible at once. By respecting the rigid limits of human working memory, we can finally begin to build systems that fulfill the original promise of the digital network.